Hi guys. So before we talk about the properties of all of these different types of salads, we have two other salads to actually introduce you to. So network salads are pretty cool because instead of being molecules that are held together by attractive forces, by IMFs, we have these big networks of molecules held together by covalent bonds. So instead of just attractive forces holding the nonmetals or the molecules together, we have these really strong bonds. So when you think about the properties of a regular molecular substance, a network solid is going to have properties that are a lot different. So the best example that I like to think of is a diamond. Um, and you can think about like how a diamond is hard and rigid. It has a high melting point. It's not easy to melt diamond. It doesn't conduct electricity. So all of those properties for diamonds are pretty common for or all network solids. So that's what makes it easier to remember the properties is to think of an example. So when we say that there are no separate particles present, if you look at every single carbon atom in this diamond example, every single carbon atom is bonded to four other carbon atoms, making this giant network, this giant crystal with this very rigid and hard structure. Okay, so that's what's responsible for giving it those properties. Over here, I have graphite. And what's cool about both of these examples is that they're both made of carbon. But if you look at the properties of graphite, you'll see how they're very different from diamond. Graphite is in your pencil. Graphite is like black and it's like slippery. Diamond is clear and it's hard. Diamond does not conduct electricity. Graphite actually has electrons that are moving around inside of it. So electricity is actually able to flow through graphite, which is not common for anything that's made up of nonmetals. So structure plays a very, very important role in properties, which is like kind of what we're getting to. Before we like move on to anything else, this is just kind of like a little side note here that's important to address. Diamond and graphite are considered to be allotropes of one another. And you guys, you don't really have to know the word allotrope. Well, I know for the regions you don't, but you have to understand the idea behind it. So, to give you another example and then see if you can think of a definition, oxygen and ozone are also allotropes of one another. So, look at what they have in common. They're both made of oxygen, but oxygen is O2. That's the pure form of oxygen, and ozone is O3. So we have O2 and O3. So look at how those molecules are different, and then I want you to compare their properties. So if these are allotropes of one another and diamond and graphite are allotropes of one another, what do you think it means to be an allotrope? So it means that they're made of the same element, but because they have different structures, so the way that the atoms are arranged is different, that's going to make them have different properties. So just because things are made up of the same stuff doesn't mean they need to be the same. It depends on how things are bonded, what types of intermolecular forces are present, things like that. So that's something that's important. Metallic bonding is something we have not talked about yet either. And a metallic bonding is very simple. Basically, it's when you have metal only. And you don't even have to think like, oh, it's a compound of metals. It can just be like one metal. So, like, for example, silver. If they give you silver as an example and ask you what kind of bonding is in silver, you can say metallic bonding. It doesn't have to be a compound because when you picture like a silver piece of jewelry, right? think about how many atoms, how many silver atoms make up that piece of jewelry. Those atoms have to be held together in some way, and they're held together by metallic bonding. So what happens is metals have low ionization energies, right? They like to lose their valence electrons to get stable. So when you have a bunch of metal atoms get together, that's what they all do. They all lose their valence electrons, and then the valence electrons kind of move around within the sample. So again, in class, when I see you guys, I will show you an animation of this. But all those negative signs in this diagram, those are electrons, and I want you to imagine them constantly moving around. It's called a sea of mobile electrons, metallic bonding, and they're moving around between positive ions, because when atoms lose electrons, they become positive. So if you think about like, why is this able to stick together? You have positive ions and negative electrons in the same sample. So whenever you have things that are oppositely charged, they're going to be attracted to each other and they're going to stay close together. Okay, so that's what metallic bonding is. All right. Can a compound contain more than one type of bond? Yes, it can. So I want you guys, in the examples that I'm giving to you, I want you guys to think about what the formulas of these compounds are. So when calcium bonds to the nitrate polyatomic ion, the formula looks like this. So how is calcium bonded to the NO3 ion? This is an ionic bond. Calcium is a metal. NO3 is a non-metallic polyatomic ion. So we have a metal to a non-metal, a positive ion to a negative ion. So there's ionic bonding. But then within the polyatomic, I have N bonded to 3 O's. N is a nonmetal and the O's are nonmetals. So what kind of bonding do I have here? I have covalent. So guys, anytime you have a compound that has a metal and a polyatomic ion in it, you guys have been studying your polyatomic ions, right? You knew that sulfate was SO4, right? You're always going to have the ions being attracted to each other by ionic bonding, and then within the polyatomic, you're going to have just nonmetals, so it's going to be covalent. So that's just something, you're never going to have to like draw one of these, but you have to be able to recognize if a compound is complicated enough to have more than one type of bond in it. You want to look for at least 3 capital letters. If you only have 2, then there's only room for one kind of bond. Okay. So finally, guys, now that we've talked about network solids and metallic solids, we can kind of summarize with this big giant chart that tells us the general properties of all these things. So let's kind of like talk about the type of solid first. When you see the word molecular, that's going to be your covalent, your simple covalent compound. Because also with covalent bonding, you could have a network solid. So saying covalent really isn't even being specific enough. Is it a covalent compound, a covalent substance made up of molecules, or is it a covalent substance that's one big giant network? Okay. We have our ionic, which is metal plus nonmetal. We have our metallic, which is metal only. And then here, guys, we can say for both of these, non-metal only, non-metal only. Okay, so guys, if we look at the next column, form of unit particles, like what particles are present. So in everything, we have atoms, except for in ionic. Ionic, because electrons are lost and gained, we have ions. Okay. Forces between particles. So in metals, we have metallic bonding. In ionic compounds, remember talking about electrostatic attractions? That was your positive being attracted to your negative. That's what's holding the particles together. In a network solid, we have covalent bonds, where in a molecular solid, these are all IMFs. Okay. So guys, think about this column is super important for explaining properties. When you think about molecules being held together by attractions, that's a lot weaker than things being held together by bonds or positive and negative ions or positive ions and negative electrons. These bottom three types of solids, their properties are going to be a lot stronger, I would say, compared to your molecular substances. Okay, so let's jump over to these properties. As far as you guys being able to do this, if you're given a substance and you don't know what elements make up that substance, then you really can't say what kind of bonding there is. But if you do some tests and find out some properties about the substance, you can make some assumptions about its type of bonding and what kind of solid it is. So I'm just going to highlight like some important words. Covalent compounds, molecular compounds, they're usually soft. They have a low melting point and poor conductors. Now guys, these are just general properties. Of course, there's probably always some exceptions, but in general, this is what you're always going to see associated with something that's considered a molecular solid. Okay. As far as solubility goes, solubility isn't on this chart, but I'd like to add it. If it's a polar substance, it's soluble in water. And if it's a non-polar substance, it's insoluble in water. So again, this is something that we're going to talk about again in another unit. But water is polar. It has a positive and a negative side. And in order to dissolve in water, you have to be like water. You have to be similar to water. You also have to be polar. So for molecular compounds, their solubility depends on whether or not they're polar. Okay. For your covalent network, guys, you want to think of diamond. So you want to think hard. You want to think high melting point, but still a poor conductor. So there are ways to tell the two different types of covalent things apart. Conduction is bad for both, but the melting point and the hardness will help you tell it apart. Okay. For ionic bonding, and we could also say, guys, I'm sorry, they're insoluble in water. All right. For ionic, they're hard, brittle, high melting and boiling point. I don't like, actually, I know why it says. So it says poor conduction because this table is talking specifically about solids, right? But there's something very unique about ionic compound. They're actually good conductors if you melt them and they're a liquid, or if you dissolve them in water and make an aqueous solution out of them. So why is that the case? We talked before about how to conduct electricity, you need charged particles that are moving. And in ionic compounds, you have charged particles. You have positive and negative ions. But in the solid phase, they don't have a lot of motion. If you melt it and make it a liquid, or if you dissolve it in water, now the particles are free to move and they can carry electric current through them. So that's a big property that like really makes ionic compounds stand out from the rest as far as like testing goes. For metals, I don't like to be specific about the hardness of metals because some are very soft and some are very hard, so that depends. I don't even like really how it says low to very high melting points. There's like one metal, gallium, that can like actually melt in your hand. It has a ridiculously low melting point. But as far as like general properties, metals are not easy to melt. So typically, what you're going to see if you're asked about properties is high melting points for metals. Excellent conductivity. So, again, guys, this is what's going to separate your metal from everything else here. Metals conduct in any phase, as solid or liquid, and that's how we can tell it apart from ionic compounds. And finally, we're going to add that they're insoluble in water. Okay. So you can think, guys, if I put you in the lab and I gave you some stuff and I asked you like to tell me what kind of solid it is, you'd want to think about some of these tests that you can do that could really help you narrow it down. All right. So that is it for properties. I'm going to give you guys one last question and I will see you tomorrow.